In front of you, you see an exam that I gave to my Calculus 1 class, face-to-face class. This is their test number 2. We're going to go through the solutions to this exam. So the first question says, find the derivative of the following functions. Part A says y is equal to cosine of z squared times e to the 2z. So looking at this, I noticed that we're going to need to use the chain rule. Our outer function here is cosine of this z squared e to the 2z. So when we're taking the derivative, we take the derivative of our outer function. So the derivative of cosine is negative sine. Keep the inner function the same, which would be z squared e to the 2z. And then we're multiplying by the inner function, and our inner function in here, and we're multiplying by that derivative of the inner function. So the derivative, we can write this as d dz, we haven't taken it yet, of the inner function, which is z squared e to the 2z. So looking at this, we get y prime is equal to negative sine z squared e to the 2z times the derivative of the inner and the derivative of z squared. And notice when we're looking at the derivative of the inner, we need to use the product rule. So the derivative, think of the first piece as z squared, is 2z times the second part, e to the 2z, plus the first part, z squared, times the derivative of e to the 2z. So when we're using the derivative of e to the 2z, again, we need to use the chain rule, which says take the derivative of the exponent, which is 2, times the original function itself, which is e to the 2z. I was okay if you left it like this. You could, if you wanted to, distribute, but I was good with that. So number 1, part B wants us to find the derivative of y is equal to the natural log of the following. 1, all divided by the quantity, x times the square root. Underneath the square root, we have 1 minus 2x. So again, I noticed that we're going to need to apply the chain rule here. But if we first rewrite this using rules of logs, we're going to make our life a lot simpler. So let's do that. Let's rewrite y equals the natural log. So recall if you had division of what you were taking the natural log of, we could look at the natural log of the numerator minus the natural log of the denominator. So natural log of x times, I'm going to rewrite the square root as a 1/2 power. So rewriting the square root of 1 minus 2x, I have 1 minus 2x. And that 1 minus 2x is raised to the 1/2 power. So now notice that we can rewrite this a little more, because that second piece, what we subtracted off, the denominator, has a multiplication in between. And so multiplication, when we have a natural log of multiplication, we're going to rewrite that as addition. So natural log of the first piece, be careful, we need parentheses around that whole natural log. We have natural log of x plus the natural log of the second piece, which is 1 minus 2x to the 1/2. I can distribute this negative. And again, I can use rules of exponents, rules of logs, which says I can bring my exponent down front. So rewriting this, I have, this is y is equal to the natural log of 1 minus the natural log of x minus, bringing down my power, 1/2 natural log of 1 minus x minus 2x. So let's go through now and take the derivative of this, and using the rule of derivative of logs. So let me write that up here, maybe over here. So if we had y is equal to the natural log of g of x, the rule says that when we take the derivative, it's 1 over what we were taking the natural log of g of x times the derivative of the inside. So in our case, g prime of x. So using that rule while we go through to take the derivative, y prime equals, well, the derivative of natural log of 1, that's just a constant. That's just a number. So the derivative of a constant, recall, was 0, minus the natural log of derivative of natural log of x, which is 1 over x, minus 1/2 times the derivative of the natural log of 1 minus 2x. So that would give us 1 all over what we were taking the natural log of, 1 minus 2x, times the derivative of the inside, which is -2. So notice that we can simplify here a little bit. The 2's cancel in our numerator denominator, and I have a minus a negative, which is going to be a plus. So our derivative function y prime is equal to -1 over x plus 1 over 1 minus 2x. If you're in my class right now and you're doing an assignment where you're asked to have taken this as an exam and then go back through and grade your practice exam, the first problem, 1A, was worth 5 points. I'm going to put 5 points on the side. This was worth 5 points, and 1B is worth 6 points. Okay, so moving on, we have 1C, where we want to find the derivative of y is equal to the cubed root of the following: x all times x minus 2 quantity squared, and then that is all over x cubed plus 1. All of that is underneath the radical. So looking at this, we'd have to apply so many different rules while we went to take the derivative. We'd have to apply the chain rule, the quotient rule. Within the quotient rule, we'd have to apply the product rule. And within that product rule, we have to apply the chain rule. So that would be kind of messy and ugly. And so we can use logarithmic differentiation. So let's do that. Let's first take the natural log of both sides of this equation, rewrite the one side using properties of logs like we had done in the example above, and then take the derivative. And so if we took the natural log of both sides of our equation, we have the natural log of y is equal to the natural log. While we rewrite this, instead of writing the cubed root, we're going to rewrite it to the 1/3 power. So we have the natural log of x all times x minus 2 quantity squared. That's all over x cubed plus 1. And that whole thing is raised to the 1/3 power. So now let's go through and use properties of logs to rewrite this. So bringing down the natural log of y, this is equal to, well, rules of logs says that we can bring our exponent down front. And so this is going to give us 1/3 natural log. I notice I have a quotient here, x all times x minus 2 quantity squared. And this is all over x cubed plus 1. So again, rules of logs, if we have a quotient, then we can rewrite that as a difference of 2 logs. That 1/3 needs to be in front of both the numerator and denominator when we rewrite it as logs. So we have the natural log of y is equal to 1/3 of the natural log of our numerator, which was x all times x minus 2 quantity squared, minus that 1/3 needs to carry 1/3 natural log of the denominator, which was x cubed plus 1. So bringing down the natural log of y, that first natural log, notice that we have multiplication between that x and the x minus 2 quantity squared. So we're going to write that using properties of logs. And multiplication, we rewrite as addition. So we have 1/3 natural log of the first piece x plus that 1/3 would have distributed. So 1/3 natural log of x minus 2 quantity squared. And then bringing down the minus 1/3 natural log of x cubed plus 1. So again, we can use rules of exponents. And we can bring that 2 down for that 1/3 natural log of x minus 2 quantity squared. So rewriting this one more time, we have the natural log of y is equal to 1/3 natural log of x plus 2/3 natural log of x minus 2 minus 1/3 natural log of x cubed plus 1. Okay, so now we're going to use implicit differentiation to take the derivative of both sides. So taking the derivative of the natural log of y, well, that's 1/y times dy dx. This is equal to, so taking the derivative of the other side, so derivative of 1/3 natural log of x is 1/3x plus 2/3 times the derivative of the natural log of x minus 2. So that's 1 over what we are taking the natural log of, x minus 2, times the derivative of x minus 2, which is just 1, minus 1/3 times the derivative of the natural log of x cubed plus 1. That's going to give us back 1/x cubed plus 1 times the derivative of x cubed plus 1, which is 3x squared. So we can rewrite this. I'm going to multiply both sides of my equation. I want the derivative. I don't want 1/y times the derivative. We're going to multiply both sides of the equation by y. But recall, this is what y is. So when we multiplied on that right side, let's just define it as what it was when we originally got it. So we found that the derivative dy dx is equal to 1/3x plus 2/3 times the quantity x minus 2 minus, so notice over here, this third grouping, the 3's cancel in the numerator and denominator, and we would be left with x squared all over x cubed plus 1 all times y. But again, we were given that y was the cubed root of x. That x is times x minus 2 quantity squared underneath the radical. Still underneath the radical, that is put over x cubed plus 1. So if you're in my class and you are grading your exam, this part C was worth 7 points. So moving on to number 2. So number 2 states y is equal to sine inverse of 1 minus x. Derive the derivative without plugging it into the derivative of the inverse of trigonometric formulas. You can use this as a check if you like. Okay, so instead of just using the formula and plugging in, I wanted you to derive this. So in class, what we were looking at is we didn't know how to take the derivative of the inverse function. But if we took, in this case, the sine of both sides, we know how to take the derivative of sine. So in this case, let's get rid of that inverse function by taking the sine of both sides of our equation. So I'm looking at sine of y is equal to sine of sine inverse of 1 minus x. So this gives us sine y is equal to, well, function composed with a composition of its inverse function that cancels out. And so we're just left with 1 minus x. I'm going to treat this like a ratio so I can create a triangle. So 1 minus x, I'm going to put all over 1. So let's create a triangle, and then we'll go back and finish this problem and take the derivative both sides. So let's create a right triangle. Let's put in our angle y into one of the angles that is not the right triangle, or right angle. And then we know sine is opposite over hypotenuse. So opposite of the angle that you chose is 1 minus x. The hypotenuse, the angle across from the right angle, is 1. And so now let's find that adjacent side of y. And so using the Pythagorean theorem, we know that, let me maybe call it b here. 1 squared is equal to 1 minus x quantity squared plus b squared. Getting b by itself, we got b squared is equal to 1 minus the quantity 1 minus x quantity squared, and then take the square root of both sides. We're talking about length, so we're only looking at the positive value. Okay, so now we have our triangle. Let's go back and let's differentiate both sides. So we're checking the derivative of sine y. And so we're going to need to apply the implicit differentiation. And so derivative of sine, I know, is cosine. So we have cosine y times the derivative of the inside, which we're going to call dy dx, is equal to the derivative of 1 minus x. Well, derivative of 1 minus x is just -1. Let's get dy dx by itself by dividing both sides of the equation by cosine of y. So we get dy dx is equal to -1 all over cosine of y. Now let's go back to the triangle that we created and let's figure out what cosine of y is. Well, cosine of y, this is adjacent, which is our b value. What b in this case we found was 1 minus the quantity 1 minus x quantity squared, all over the hypotenuse, which is 1. So we have -1 all over cosine of y. The cosine of y we just saw was the square root of 1 minus the quantity 1 minus x quantity squared. So that is the derivative of sine inverse of 1 minus x. So for this problem, this were 6 points. So going to number 3. Number 3 states, use implicit differentiation to find dy dx of x minus y quantity squared equals x squared minus y squared. So when we use implicit differentiation, notice that when we take the derivative of the left-hand side, we're going to need to use the chain rule. Whenever we take the derivative of y is a function of x, and so we need to tack on the derivative of the inside, which is dy dx. Okay, so let's take the derivative of the left-hand side, the quantity x minus y, quantity squared. That's going to give us 2 all times x minus y. Subtract 1 from our exponent, we get 1 times the derivative of the inside. So derivative of x is 1 minus the derivative of y is 1, but that was a function of x, so we're going to tack on that dy dx. This is equal to, so taking the derivative of the right side, derivative of x squared is 2x minus the derivative of y squared is 2y dy dx. So we're trying to find dy dx. So we're trying to get any term that has dy dx all by itself. So let's kind of distribute on this left-hand side of our equation. So rewriting this, we have 2x minus 2y, distributing that 2 in there, all times the quantity 1 minus dy dx is equal to 2x minus 2y dy dx. So distributing on the left-hand side, distributing the 2x to each term in the second parentheses, we get 2x times 1 is 2x minus 2x times dy dx Now distributing the negative 2y to each term in the second parentheses, we get negative 2y times 1 is negative 2y. And negative 2y times a negative dy dx is a plus 2y dy dx. This is equal to the other side of our equation, 2x minus 2y dy dx. So I get all the terms with dy dx on one side, and I want to get all the terms without the dy dx on the other side of the equation. So let's subtract 2x on both sides. Let's add 2y to both sides. And let's add 2y dy dx on both sides. So my goal was to get all the terms with dy dx on the left-hand side of my equation. So doing that, I got negative 2x dy dx plus 2y dy dx, actually 2y plus 2y, so 4y dy dx. Is equal to, well, 2x minus 2x cancels out, and then I just have the 2y left on the right-hand side. We can factor out the dy dx on the left-hand side. So pulling that out, I have dy dx times the quantity, negative 2x plus 4y. And that is all equal to 2y. So divide both sides by that negative 2x plus 2y. So we get 2y all over, I'm just going to rewrite the order. Instead of writing negative 2x plus 4y, I'm going to write it as 4y minus 2x. I notice I could factor out a 2 in the denominator. So 2 times the quantity 2y minus x. And if I do that, then I can cancel out the 2 in the numerator and the 2 in the denominator. So our solution, we found that dy dx is equal to y all over 2y minus x. So this problem also is worth 6 points. Moving on to the next problem. Our next problem, number 4. So we have this piecewise function, and it says for what values a, m, and b does the function f of x equals, our first equation is 3, when x is equal to 0. Our second equation is negative x squared plus 3x plus a, when 0 is less than x is less than 1. And our third equation is mx plus b, where 1 is less than or equal to x is less than or equal to 2. We're looking for those values a and b, m and b, that satisfy the hypothesis of the mean value theorem on the interval 0 to 2. And then I gave you a hint. That means we need to make sure that our conditions 1 and 2 below, and I gave you the mean value theorem, hold true. So we need to show that our function is continuous on that interval 1, 2, and we need to show that it's differentiable on the open interval 1, 2. If that's the case, then we know that the hypothesis is satisfied and we can use the mean value theorem. So notice that the value 3, that is continuous, or it's at x equals 0, only if it's the same value as if we took the limit on the right-hand side of 0. So if I look at the limit as x is approaching 0 on the left of f of x, this is giving me a value of 3. And it's actually an n value. If I look at the limit as x is approaching 0 on the right, that tells me to use the second equation, negative x squared plus 3x plus a. So if I went in and I did direct substitution, I would get that limit is equal to A. So my limit on the left and my limit on the right have to be the same. So 3 has to equal A. So it just happened to fall out that we got what A was right away. We need to show that it's continuous when X is equal to 1. So same sort of idea, that limit as X is approaching 1 on the left, which tells me to use the second equation, negative X squared plus 3X plus A, has to equal the limit as X is approaching 1 on the right-hand side. Our right-hand side, that we're using the third equation, mx plus b. So let's go in and do direct substitution. If I plug in 1 wherever I see an x, I get negative 1. That 1 is just squared, plus 3 times 1, plus a. This has to equal m times 1 plus b. So let's simplify that one side of the equation down. We get negative 1 plus 3, so that is 2 plus a. But we were given, or we found what a is. A was 3. So we got 2 plus 3 is equal to m plus b. So we're given that 5, or we found that 5 must equal m plus b. Okay, well, we figured out what a was, but we don't know what m and b are yet. But let's go to the second condition of our hypothesis, which says that f of x has to be differentiable on this interval. So we know that the derivative, so let's find the derivative of the second equation. So the derivative for the piece where the second equation, let's just take it, is derivative of negative x squared is negative 2x, plus the derivative of 3x is 3, plus the derivative of a, well, derivative of that constant is 0. That must be the same as if we took the derivative of the third equation when we evaluate that at x equals 1. So f prime of x of the third equation, well, the derivative of mx is just m, plus the derivative of b, which is 0. So f prime of 1, plugging in 1 in here, wherever we see an x, we get negative 2 times 1 plus 3, which is 1, must equal f prime of 1 over here. There's no x there, so that's just m. So we have 1 must equal m. So to be differentiable, this has to hold true at 1. It's differentiable everywhere else. And so now that we know what m is, we can plug in 1 for m and figure out what b is. So plugging in 1 for m, we get 5 is equal to 1 plus b. So b is equal to 4. So we found that the three values, a, m, and b, to make this following we made the following conditions possible, true, so that the mean value theorem held true. So looking at this, let's say that this was worth 10 points. Problem 4 worth 10 points if you're grading this. So moving to the next question. So given the sign patterns for a twice differentiable function, y equals f of x, answer the following questions. So we're given an interval, we're given that y prime, it's negative from negative infinity to negative 3. It's positive from negative 3 to 0. It's also positive from 0 to 2. And it's negative at 2. We have the second derivative is positive from negative infinity to negative 2. It's negative from -2 to 0. It's positive from 0 to 1, and it's negative from 1 to infinity. So finding the intervals where f of x is increasing and decreasing. Well, we can tell where a function is increasing and decreasing based off the first derivative. The values in here where the first derivative, notice we're given that first derivative is negative, is where our function will be decreasing. So we are decreasing. So looking at the first derivative, it's decreasing from negative infinity to -3, because our derivative is negative there, union 2 to infinity. It's increasing where our first derivative is positive. So it's increasing from -3 to 0, and then union 0 to 2. If you had just stated -3 to 2, I would have given you full credit. Part A, this is worth 5 points. So on what interval is the function concave up and concave down? So that has to deal with our second derivative. So concavity, if our double derivative is greater than 0, it's concave up. So looking at this, I see that it's concave up. Second derivative is greater than 0 from negative infinity to -2, union 0 to 1. It's concave down where the double derivative is less than 0. So looking at the table, I see that it's less than 0 from -2 to 0 and from 1 to infinity. This 2 is worth 5 points. So looking at the next part of that question, we're going to put together part A and B plus the other information given to us about the graph, and then we're going to graph it. So putting together the information above, sketch the graph y equals f of x that passes through the points -3, -2, -2, 0, 0, 1, 1, 2, and 2, 3. So let's first go through and let's plot those points and then put together the information that we just got. So we know we have a point at -3, -2. We have a point at -2, 0. We have a point at 0, 1. We have a point at 1, 2. And we have a point at 2, 3. So it's telling me it's decreasing until I hit x equals -3. So I'm decreasing, and then from negative infinity to -2, I know I'm concave up. And so for that piece, I'm coming down, concave up. At x equals -3, I'm starting to increase, still concave up until I hit x equals -2. And then my piece is concave down. So from -2 to 0, I'm concave down, but I'm still increasing. From x equals 0 to x equals at x equals 1, I'm from 0 to 1, I'm concave up, and 0, 1, I'm still increasing. So I'm going to change concavity, but I'm going to increase. And then at x equals 1, I'm going to change concavity again. I'm going to be concave down, I'm still increasing until I hit x equals 2, and then I'm decreasing, but I'm going to stay concave down. So your picture should look similar to this. And this was worth 7 points. Okay, so number 6. Given g of x is equal to e to the negative x squared on the interval -2, 1, answer the following questions. Find the absolute maximum and minimum values. Okay, so we have a continuous function, e to the negative x squared on a closed interval. So by the extreme value theorem, there must exist an absolute maximum and an absolute minimum on that interval, and it could occur at the end value of that interval. So we want to take the derivative and we want to find any critical points that fall between -2 and 1 if it occurs. So I'm using the rule of derivative of my e. So the derivative of e is e itself and the times the derivative of the exponent. So looking at negative x squared, that exponent, the derivative is -2x times the function e itself, e to the negative x squared. If I'm looking at this, my critical values is when my derivative is equal to 0 or undefined. This is defined everywhere, so I'm okay. So looking at when this is equal to 0, let me rewrite this a little bit. I have -2x, making my exponent positive on e to the negative x squared. I can bring that down to the denominator. So I have e to the positive x squared exponent in the denominator equals 0. If I multiply both sides of my equation by 0, e to the x squared, I would get -2x equals 0. The other thing that I could have done here, which might be a little better, is we could also look at when is -2x equal to 0, and when is e to the negative x squared equal to 0. -2x is equal to 0 when x is 0. If you look at your e function, there's no value. If I multiply, like I rewrote it before, multiply both sides by e to the x squared, I get 1 equals 0, which is false. So this is impossible for e to the negative x squared to equal 0. So we only have one critical value, and that one critical value, x equals 0, you need to make sure falls in our interval of -2, 1, which it does. So the next piece of this was, let's plot our points at those values at the end and our critical value. So we have an endpoint of -2. We have one of our critical values, x equals 0, and we have x equals 1. Plugging it back into the original function, e to the negative x squared. So g of -2 is e to the -2 quantity squared is 4. So I have e to the -4 exponent. G of 0 is e to the -0 squared, or e to the -0, which is just 1. If I plug in 1 wherever I see an x, so g of 1 is e to the -1 quantity squared is 1. Okay, so I know I have an absolute max occurs at x equals 0, which is 1. And then my absolute min occurs when x equals -2, and it's 1 over e to the -1 power. If you plug this in the calculator, you would see that this is approximately, let me just make sure real quick. Okay, so e to the -4 power gives us about approximately back 0.02. E to the -1 power, that was approximately 0.37. And that's just going to help us for part B, where we need to graph the function. So graph the function, identify the points where the absolute extrema occur and include their coordinates. So we have these points in here, and we can go a little further with our graph by finding concavity. So when x equals -2, we got about, I'm going to make one up here. We got something really close to the x-axis, 0.02. When x was 1, we got 0.37. I'm just estimating on here. And when x was 0, we had 1. Let's take the second derivative and let's find concavity if we can. Well, we can. So taking the second derivative, notice that we're going to need to use the product rule. So derivative of a negative 2x is negative 2 times the second function, which is e to the negative x squared, plus negative 2x times the derivative of e to the negative x squared. And that's going to give me negative 2x times e to the negative x squared. So this is 2 e to the negative x squared. Negative times negative is positive, so plus 4x squared e to the negative x squared. We can factor out an e to the negative x squared from both of those terms. That would leave us inside the parentheses 2 plus 4x squared. This was a negative 2 here. So technically, e to the negative x squared, this is not equal to 0. We just talked about that from above. So we're only worried about when is negative 2 plus 4x squared equal to 0. Well, setting that equal to 0, adding 2 to both sides, we get 4x squared. We're looking at when is 4x squared equal to 2, divide both sides by 4. I'm looking at when is x squared equal to 1/2. Taking the square root of both sides, I get plus or minus 1 over root 2. If we look at that, a negative 1 over root 2 and a positive 1 over root 2, and we look at our intervals, we want to see, are we concave up or concave down? So we're plugging these values into the second interval. So let's look at what is negative 1 divided by square root of 2. That gives me about negative 0.7. So I want to choose something between negative 2 or negative 0.7 and negative 2. So what about x equals negative 1? Plugging that into the second derivative, I want to see, is that going to be positive or negative? Let's plug it into this piece here. I just care, is it positive or negative? So e to the negative 1 power, that's positive. If I square my negative 1, that's positive. That time 4 is 4 minus 2, so that's positive. So this is greater than 0. If we choose a value, so let's say between negative 1 root 2 and 1 root 2, so let's say x equals 0, and we plug that into the second derivative, I notice that's going to be negative. If I choose something between 0.7 and 1 and I plug it in, it ends up being, I believe, positive. But let me check really quick. So if we plug in, let's say 0.8, I would get 0.8 quantity squared, which is 0.64 times 4. That is 2.56 minus 2 is a positive number. Okay, so we have something that is concave up until we hit negative 0.7 about. Then we're concave down, so increasing. And then we're decreasing. And once we hit 0.7, we're concave down, and we're going to change to concave up. So our graph looks similar to this. So I might be wrong, but let's say that this was 4 points. So give yourself 4 points if you got part A right. Part B is also 4 points. Looking at the last question of this exam, we have a related, or we have an optimization problem. Actually, so actually we have a related, I don't know what type of problem this is anymore. Let me read it and let me tell you then. A 15-foot ladder is resting against the wall. The bottom is initially 10 feet away from the wall, and it's being pushed forward towards the wall at the rate of 1/4 feet per second. How fast is the top of the ladder moving up the wall 12 seconds after? we start pushing. Okay. So let's draw a picture. We have some wall here. We have some ladder initially that is leaning up against the wall. And the distance between the wall and the ladder we're given to start with before we start pushing is 10 feet. The ladder we're given is 15 feet. That is a constant. It's not changing. And let's call the height y. We're pushing the ladder in, so that distance, that base that on the floor is changing, it's shrinking. And so that rate of change, we're being pushed towards the wall, is a quarter foot per second. So I know that, and maybe we can call this x. So rate of change, dx dt with time is equal to -1/4 foot per second. I can use my Pythagorean theorem. I know that y squared plus x squared is equal to the hypotenuse, which is going to be, and that's always going to stay the same, 15 squared. Let's look at what x is when we are 12 seconds after we start pushing. Well, let's see that distance that we pushed it. Well, we know that distance is equal to rate times time. We're trying to find that distance is equal to the rate that it's changing is -1/4 feet per second times the time, which is 12 seconds. So the distance that this ladder has moved is 3 feet and -3 feet. So our new distance of our base is 10 minus 3, which is 7 feet. So we know x is equal to 7 feet after 12 seconds. So we want to figure out what is that height of the ladder. Well, that ladder is extending up. As we push it up against the wall, that height is increasing. We call this y, and this is 15. So let's figure out what y is after 12 seconds. So we get y squared plus 7 squared equals 15 squared. We get y squared plus 49 equals 225. Y squared is equal to 225 minus 49 gives us 176. Taking the square root of both sides, we get the square root of 176. So we know what x, we know what y is, we know what the rate of change is for x. Now we're trying to find out what is the rate of change of that height, that rate of change of y. So let's go back to our Pythagorean theorem that we had set up, and let's use implicit differentiation. So taking the derivative of 2y, taking the derivative of y squared, we get 2y times dy dt plus derivative of x squared is 2x dx dt. And the derivative of 15 squared, derivative of a constant, is 0. So let's go back in and substitute what we have. 2 times y. Well, y is square root of 176 plus 2 times x. Well, x in this case is 7 times dx dt, but dx dt is this -1/4 is equal to 0. And I forgot to write down my dy dt in here, which we're trying to find. So we have 2 times the square root of 176 times dy dt. So getting dy dt by itself and simplifying at the same time, that 4 and the 2 cancels. So let's add 7/2 to both sides. And let's multiply both sides by 1/2 root 176. So dy dt is equal to, we get 7/4 square root of 176. We can simplify this, which is approximately 0.1319 feet per second. So the height of that ladder is increasing that much. How many feet per second? At 12 seconds after we start pushing the ladder up against the wall. So this problem is worth 10 points. So sum your score. All the points total for this test was 75 points. So put your score that you got over 75 points. And then also give me your percentage of that grade. So if you were doing this as an assignment in my class by grading your exam, you're putting your score over 75 and the percent that you got on that test, and you're uploading that to your Canvas assignment. I'm just going to stop that recording.